Engine timing. The timing of valve opening and closing is extremely important to the life and performance of an engine. In this unit, we will discuss the effects of opening a valve earlier or later has on an engine. Valve events, camless engine, cam and crankshaft correlation, and timing components. In order for the valves to open at the correct time to keep them from making contact with the piston, the cam and crankshaft have to be timed perfectly. Using a degree wheel, we can make minor modification in cam timing to change the RPM range of the camshaft's power range. Exact camshaft to crankshaft timing or correlation is required to keep the valves from coming into contact with the pistons. Camshaft duration is the open time of the valve. This is normally measured at 50 thousandths of an inch of lift. Now that we understand the importance of correct cam timing, let's talk about the individual valve events. In this picture, we're graphing the pressure behind the intake valve, behind the exhaust valve, and inside the combustion chamber. Pumping loss is a bad thing. It is the wasted energy being used to force the exhaust gases out of the cylinder because we didn't open the exhaust valve early enough. We can take advantage of the pressure that is built up behind the intake valve to force air into the cylinder. This is created by intake design. Notice the degree range of crankshaft rotation that the intake valve closes, the intake valve opens, the exhaust valve closes, and the exhaust valve opens. The exact time will depend on RPM you want the engine to make the most power. Also notice the valve overlap. This is the time in which the intake and exhaust valve are both open at the same time. More overlap will indicate a higher RPM range of power. Intake valve opening can range anywhere from top dead center to 21 degrees before top dead center, depending on what RPM we want the camshaft to operate. Lower RPM power, we want to open it at top dead center. Higher RPM power, we want to open it earlier, 21 degrees before top dead center. Exhaust valve closing, anywhere from top dead center to 15 degrees after top dead center. Top dead center for lower RPM torque, after top dead center for higher RPM power. Exhaust valve opening. Keep in mind the exhaust valve opening is happening on the power stroke. So the earlier we open the exhaust valve on the power stroke, the shorter the power stroke is. But due to pumping loss, if we open the exhaust valve too late, the piston is going to be shoving up on pressure, which is robbing us of power. So lower RPM engines, we're going to open it close to bottom dead center. Higher RPM engines, we're going to have to open it at 57 to 60 degrees before bottom dead center. Intake valve closing is happening on the compression stroke. So the later we close the intake valve, the shorter our compression stroke. Lower RPM engines, we're going to close close to bottom dead center. Higher RPM engine, we're going to leave it open to take advantage of the incoming air behind the intake valve. This is, we're going to close it 51 degrees after bottom dead center. advanced cam timing at low RPM for better throttle response and torque. Valve duration can also be increased at higher engine speeds to improve breathing. Retarding cam timing when the engine is under a load to reduce oxides of nitrogen emission and to eliminate the need for an EGR valve. Looking at the profile of a diesel engine, it's not much different than a gasoline engine. You'll see that the intake valve opening at 25 degrees before top dead center, intake valve closing 30 degrees after bottom dead center, exhaust valve opening 45 degrees before bottom dead center, and exhaust valve closing 15 degrees after top dead center with an overlap of 30 degrees is not much different than a gasoline engine. In fact, it falls right into the range that we just went over of gasoline engine. Now let's take a look at three different cam profiles from competition cam. The first one being what we're used to refer to as an RV cam, which is a little bit higher RPM range than stock. If you notice, the intake valve opens about 9 degrees before top dead center. The intake valve closes at 50 degrees after bottom dead center. On the exhaust side, the exhaust valve is going to close at 17 degrees after top dead center, and the exhaust valve opens at 50 degrees before bottom dead center. And we have an overlap of 26 degrees. This is just a little bit above a stock cam. Duration is not real high. The intake valve is opening close to top dead center. The exhaust valve is closing relatively close to top dead center. Taking a step up, this is competition's 268 cam. This is the first what they consider their high energy cams. If we notice, our intake valve now is going to open at 28 degrees before top dead center, and it's going to close later at 60 degrees after bottom dead center. Even though this says BBDC, it's supposed to be after bottom dead center. Our exhaust valve is going to close about 20 degrees after top dead center, and it's going to begin opening earlier at 68 degrees before bottom dead center. This is to help prevent any pumping loss on the compression stroke. Overlap is now increased up to 48 degrees. Okay, now let's move to the big one. Looking at the specs on this one, Pro Street, bracket, limited street driving, intake, gears, 3,500 plus stall converter. Racy idle, 10.5 to 1 compression ratio. Drag racing requires a 3,500 to 4,000 stall converter or a 4-speed with 11 to 1 or greater compression. Okay, now intake valve. We open this thing at 40 degrees before top dead center. We've got the engine running fast enough now that we've got the intake flowing, we've got the pulses being built up behind the intake valve. On the exhaust side, we've also got a scavenge effect where the exhaust is actually assisting us in sucking some of the exhaust out of the combustion chamber or out of the cylinders. So the intake valve is going to open at 40 degrees before top dead center, and then if we come around on the compression stroke, you notice that we're not closing the intake valve until it is at 84 degrees after bottom dead center. So when we think about it, ideally, to take full advantage of the compression stroke, we're going to want to close the intake valve close to bottom dead center. But with the speed that the engine's running at, and the intake valve, the intake pulse is working, the exhaust scavenge working, we're trying to give as much time as possible for all of that air to get packed inside the cylinder. So we're not closing the intake valve until 84 degrees, high RPMs. But that is also where this 10.5 compression ratio and this 11.5 or 11 to 1 or higher compression ratio come into effect, because we're not closing that valve until this thing is way up on the compression stroke. On the exhaust side, look at the time that we're opening the exhaust valve, 80 degrees before bottom dead center. So on the power stroke, the piston's on its way down, but we're opening the exhaust valve at 80 degrees before the piston ever gets to the bottom. So we're losing on our power stroke, but we have to do this in order not to have any pumping loss on the compression side. Okay, now if we look at the overlap, 84 degrees overlap. That means that there's 84 degrees of crankshaft rotation that the intake valve and the exhaust valve are open. This is about the same effect as opening an EGR valve, letting exhaust gases back into the intake at idle. That is where our choppy or racy idle comes from. This engine's actually missing at idle. That's how come we've got to bring the RPMs up to 3,500, 4,000 RPM before it's ever going to take off. If we was to use this cam with a stock converter, we're setting at a red light, nail it to the floor, chances are we're not going to go anywhere real fast until the RPM comes up, that the exhaust starts flowing, the intake starts flowing, then it'll take off. So if we use a 3,500 to 4,000 stall converter, we're getting the RPMs up so that everything's flowing and everything will take off by the time the vehicle starts to move.